Hello, today we're going to talk about locally ringed spaces and we'll finally see what a scheme is. So let's start with the definition of a ringed space. That's quite simple. That's just a pair X, so where X is a topological space together with a sheaf on X, and the sheaf is a sheaf of rings. So a ringed space. And OX is just a sheaf of rings on X. And we'll usually call it a structure sheaf on X. Okay, now let's define a locally ringed space. So we look at the stalks. And if all the stalks are local rings, then we call the ringed space a locally ringed space. Okay, that's the definition. Let's give some examples. So first of all, you might note that we've seen a lot of spectrum of rings. So let's start with them, with affine schemes. So we have the topological space is the spectrum together with the Zariski topology. Then we need the structure sheaf, and we've seen it on the spaces of principal open set. So this was this localization, or we could also write it as AF. Okay, and so that's the sheaf on the basis, and we've seen that was a small lemma that the stalks are localizations at primes corresponding to the points. So Px is the prime corresponding to the point X, and this is a local ring. So that's indeed a locally ringed space. And we can also give another example, namely we can use manifolds. You can think of real or complex manifolds. And let's take structure sheaf. So we have several options here. So we could take, for instance, the functions that are infinitely often differentiable, or we could also take, if we're in a complex case, holomorphic functions, or you can think of other options. Just pick one of them. And now we have to check that this gives us, so that's obviously a ringed space, and it's actually also a locally ringed space. So I'll leave the details to you, but we have to check that the stalks have a unique maximal ideal, so that it's a local ring. And what is this? So this is some equivalence. Let's take some equivalence class in the stalk, and we pick the ones which are 0 at the point. And you can check that this is independent of the choice of the representative f here of this class, and also that it's the unique maximal ideal. I won't do this here, but it's not that hard to show it. Okay, so now we'll define what a morphism of ringed spaces is, and we need a little more than later to define what a morphism of locally ringed spaces is. So let's start with a morphism of ringed spaces. So what's that? That's a pair. We'll write it like this. So f b from x ox to y, and the structure sheaf on y. And now we have to specify what we mean by this. So the first part is quite easy. So the map F should just be a map of topological spaces that's continuous. And the second part is not so straightforward. So that's a morphism of sheaves on Y. So we go into the direct image. So this should be a morphism of sheaves on Y. And we'll later also see an example of this, but we first want to define a morphism of locally ringed spaces. Okay, so next definition. Let's take two local rings and let's take a ring homomorphism from A to B, and we call the homomorphism local if the inverse image of the maximal ideal in B under phi is the maximal ideal in A. Or we could also equivalently, so that's a small exercise, another condition which is equivalent to this is that the image of the maximal ideal in A is contained in the maximal ideal of B. Okay, that's a local homomorphism. And now let me give you a short reminder. So in the last video we've seen that the push forward, so the direct image, is adjoint to the inverse image. So in the case of a ringed space, we have this map from OY into the direct image of OX, but that's equivalent to giving another morphism. So this is now a morphism of sheaves on X of the inverse image to OX. Okay, and now that we have this morphism, let me remind you of something else we've seen. So we get an induced morphism on the stalks, and we've seen that the stalk of this is just basically, so that's isomorphic to the stalk. I wanted to write an X here. So the stalk here is isomorphic to the stalk of the structure sheaf on the Y at f of x. So we get a morphism from here to here. And now we are in a position to define a morphism of locally ringed spaces. So again it goes from x to y, so later we'll often omit this part here and we'll just write from x to y, but for now I'll write it completely. So that's a morphism of ringed spaces. So again we have this FB such that the induced, oops, no, what's going on here? Okay, such that the induced amorphism, so we have this morphism from y f of x to the stalk at x, and this should be a local homomorphism of rings. Okay, so now an example, and then we'll define schemes. Okay, let's take two, let's say just complex manifolds M and N. Let's take a holomorphic map between them, and the structure sheaves are just holomorphic functions. And now we want, we show that a holomorphic map induces a morphism of locally ringed spaces. So we want a map in the direct image. So direct image is by definition on open sets just this. But let me write the O better. Okay. And so here we have a map phi from U to C. And well, what do we get here? Well, we compose with F, then we are in U, and then so by checking on charts you could check that this is holomorphic, but that's not that hard to check, and which we also don't check here, but you can also check that it's a local homomorphism, and also you can check that actually giving a map of locally ringed spaces in this category, so complex manifolds, is equivalent to giving a holomorphic map. But we also won't do this here. Okay, so we've talked a lot about affine schemes, so let's make the definition waterproof now. So this is a locally ringed space x OX that's isomorphic to just the spectrum of a ring and the structure sheaf of the spectrum of a ring. And well, you can, so we've defined morphisms, so you can easily define isomorphisms in this category of locally ringed spaces. Okay, and a morphism of affine schemes is a morphism of affine schemes is a morphism of locally ringed spaces. So of course both of the objects then should be affine schemes. So it's a morphism of locally ringed spaces where say x and y are affine schemes. And now we are finally in a position to introduce the main object of study, and that's a scheme, and that's a locally ringed space X and the structure sheaf on X, and we want to impose a condition on the space, namely that there exists an open covering. So we have some UIs open that cover X, and each of these UIs is isomorphic to an affine scheme. So we have OX, we can restrict the sheaf to UI, and this should be isomorphic to an affine scheme. And a morphism of schemes is again just a morphism of locally ringed spaces, where again, if we say from X to Y, both are schemes. And in case I'm not sure, I haven't told you what this means. This means just so for OX UI of V is just OX of V for V subset UI open. So if it's an UI open, it's also open in X, and so that's the restriction. Just as a small aside if I haven't mentioned this before. Okay, so that's good. Finally, we can talk of schemes, and next time we'll probably, I'm not sure yet, so we'll see a little bit more about affine schemes and see that we have an equivalence of category between affine schemes and rings. Of course, rings again with one and commutative. And then we'll study probably some more properties of schemes and see some examples of schemes. Okay, thanks for watching. Have a good day. Bye.